Hello everyone. In this lecture, I would like to discuss vector analysis. Quantities in physics divided into two main categories: scalar quantity and vector quantity. Now, scalar quantity, it's a quantity that require only a magnitude, no direction required, like time, length, temperature, age, etc. But vector quantity, we require here two things: the magnitude and direction, like displacement, velocity, acceleration, etc. Now, the vector quantity can be expressed as bold line, like this one here. Some textbook adopt this notation, others adopt this notation. In this course, we will adopt this notation, a symbol and an arrow above that symbol. So this is called a vector quantity. Now let's start with vector algebra. Before going further in vector algebra, let's have some definitions. The first one is two vectors A and B are equal if they have the same magnitude and same direction regardless their initial and end points. Example, if we have here vector A and vector B, now if they have the same magnitude and same direction, in this case we call this one as vector A equal to vector B. As another definition we have here is the negative of the vector can be represented by an arrow equal in length but reversed direction. So if you have vector A, this one here, now minus A as a vector will be something like this. So it's the same magnitude but the direction is reversed. Now the sum of two vectors is a new vector defined as C. So if you add vector A plus vector B, the resultant is a new vector called C. Now if this is A, this one here, from the head of A we draw B, and tail to tail, head to head, this vector called C. So this is A, this is B, and this is vector C. Vector addition is commutative, which means C as a vector equal to A plus B, which equal to B plus A. So this procedure is called commutative. No. Subtraction is actually an addition, but when we subtract the vector, we actually add a reversed vector. So A minus B is actually equal to A plus minus B. So rather than having B, for instance, in this direction, so minus B, as we mentioned before, will be something like this. So when we subtract two vectors, if A this direction and B this direction, the reverse or minus B will be something like this, and the resultant vector is C. Again, tail to tail, head to head. One important note here, the geometrical representation of a vector does not depend upon any coordinate system. So let's have this situation here. If this one here is vector A, which has three components, one on X and one on Y and one on Z. In this case here, the angle with the x-axis, it's alpha, and the angle with the y-axis, it's beta, and the angle with z, it's gamma. So the components of vector A here is the intercept with the x-axis, so ax in this case here equal to a cosine alpha, and ay equal to a cosine beta, and az in this case equal to a cosine gamma. And the magnitude for vector A is square root of ax square plus ay square plus az square, or A in this case equal to, we just substitute ax, ay, az, a square cosine square alpha plus a square cosine square beta plus a square cosine square gamma, all to the power half. We can just take a out of this, so a times cosine square alpha plus cosine square beta plus cosine square gamma, all to the power half. And from this one here, we can conclude that cosine square alpha plus cosine square beta plus cosine square gamma all equal 1. Back to the equations here, we can find that cosine alpha equal to ax divided by ax square ay square az square to the power half. And if we follow the same procedure, cosine beta equal to ay divided by ax square ay square az square, all to the power half, and cosine gamma equal to az ax square ay square az square, all to the power half. Now let's define a unit vector. So vector A is actually equal to a hat, and a hat in this case is defined as unit vector. It's a vector with magnitude 1. It just give the vector a direction in such a way a hat equal to a vector over its magnitude. Or in other words, a hat equal to vector A divided by its magnitude, it's ax square ay square az square to the power half. Based on the above, we can write vector A equal to ax I hat ay j hat az k hat. In such a way, I hat, j hat, k hat are unit vectors. If we would like to find vector c equal to a plus b, in this case here, we just add I with I, j with j, k with k. Now, we can just write cx here equal to ax plus bx, and cy equal to ay plus by, and cz equal to az plus bz. Remember, we cannot add I with j. We cannot add ax with by, and so on. We just add I with I, j with j, k with k. Same thing applies when you subtract vectors. So vector c equal to a minus b. So in this case, we have to follow same procedure. So cx equal to ax minus bx, cy equal to ay minus by, and cz equal to az minus bz. Now let's have an example. If we have vector a equal to 4i minus 2j plus 3k, question, find the direction cosines of a and the unit vector in the direction of a. To solve this one, let's find the magnitude of vector a, which equal to square root of ax square plus ay square plus az square, and in this case a, or the magnitude of a, equal to square root of 16 plus 4 plus 9, or square root of 29. Now the direction cosines in this case here, cosine alpha, it's equal to the ax here divided by the magnitude of vector a, and ax, if we back to the vector right here, it's 4 divided by the magnitude for vector a, it's square root of 29. Cosine beta equal to ay over the magnitude of a, on this case here. Now ay, it's minus 2, so minus 2 divided by the magnitude, it's square root of 29, and follow the same procedure. Cosine gamma equal to az divided by magnitude of a, which equal to az, it's equal to 3 divided by square root of 29. Now to find the unit vector in the direction of a, the unit vector, equal to vector a divided by its magnitude, or 4i minus 2j plus 3k divided by the magnitude of a, its square root of 29. Let's have another example. Vector a equal to minus 4i plus 5j minus 2k. Vector b equal to 3i plus 7j minus 8k. Find the magnitude of a plus b and b minus a. Now to find a plus b as a vector, it's equal to, remember, we just add I with I, j with j, k with k. So minus 4 plus 3, it's minus 1, so minus I hat. Plus 5 plus 7, it's 12, j minus 10, k. Now the magnitude, k hat, the magnitude of a plus b, it's equal to square root of ax squared, it's 1 square, just 1, plus 12 square, 144, plus 10 square, it's 100. So it's equal to 7 square root of 5. Now to find b minus a, in this case, remember, the subtraction or vector subtraction is not commutative. So b minus a, it's not equal to a minus b. You just subtract 3 minus minus 4, it's 7, I, plus 7 minus 5, 2j minus 6, k. So far, vector A could represent any vector quantity like force, magnetic induction, velocity, displacement, or any other vector quantity. Therefore, let's define the most important quantity in mechanics and electromagnetic theory, which is displacement. And if the displacement is measured from the origin to certain point x, y, z, therefore the position vector r, it's very important here, is defined as x I hat plus y j hat plus z k hat. In such a way, x equal to r cosine alpha, y equal to r cosine beta, and z equal to r cosine gamma. Now this is the same definition of vector A as we mentioned previously, and cosine alpha equal to x over square root of x square y square z square, and cosine beta equal to y over square root of x square y square z square, and cosine gamma equal to z over x square y square z square square root. And also the unit vector r hat, or sometimes r naught, equal to the position vector r divided by the magnitude of r, which equal to x I hat y j hat z k hat divided by square root of x square y square z square. Now let's define rotation of axes. For simplicity reasons, let's define rotation of two-dimensional Cartesian system as we can see in this figure here. Now the original coordinates, it's x and y. If we rotate these coordinates by an angle theta here, the new coordinates become x prime and y prime. Now the original point is x and y, which has intercept on the x and intercept on the y. What's gonna happen for this point in terms to the new coordinates x prime and y prime. So the new position for this point in terms of x prime and y prime will be like this one here, x prime and y prime. Now x prime is the intercept of the point, this point here, with the new axis, which is x prime, this one here, and y prime is the intercept with the new y prime axis. So let's find the relation between x prime and x. So x prime in this case equal, if this is theta here and this angle here, it's 90 degrees, and this is right angle triangle. Now cosine theta, it's equal to this part here divided by this one here. And remember, this one here is the intercept for x. This one is x. So this one will be x cosine theta. If we rename this part just from here to here as M2, and we rename also this part from this point to this point as M1. In this case, x prime is equal to x cosine theta, this one here, plus M2 plus M1. So x prime equal to x cosine theta plus M2 plus M1. Now, if this is theta, this will be theta as well, because if this is theta and this is 90 degrees, so this will be 90 minus theta, so this will be equal to theta. And if this is theta, this will be theta as well. If this is L1 and this is L2, this right angle triangle, this one here, this is 90 degrees. So sine theta equal to M1 over L1, or we can say that M1 it's equal to L1 sine theta. And if we follow the same procedure, if this is theta here and this is right angle triangle, so M2 will be equal to, and this is L2, equal to L2 sine theta. Based on this, if we plug them back in this one here, so x prime equal to x cosine theta plus L1 plus L2, because it's the same angle, sine theta. Or we can say that x cosine theta plus, now L1, this is L1 and this is L2, is actually the intercept with the y. So this is y here. So from this one here to this one equal to L1 plus L2. So y sine theta. So let's keep this one here. Now let's find the relation between y prime and the original coordinates x and y. So y prime, this one here, equal to, so this is y prime, this one right here, this one, and it's the same as this dashed black dashed line, this one here, and this is right angle triangle, this one here, like this one. So y prime is actually equal to this part here, which equal to L1 cosine theta, which equal to, now L1, this one here, is actually equal to y, this is y, minus L2. times cosine theta. By simplifying this one here, y cosine theta minus L2 cosine theta. Now this is L2 and this is right angle triangle with the base here is x and the height is L2, and if we take tan theta equal to L2 over x, so assuming that tan theta equal to L2 over x, and if we substitute this back in this one here rather than using L2, so in this case y prime will be equal to y cosine theta minus x tan theta cosine theta, or remember tan theta equal to sine over cosine, so equal to minus x sine theta plus y cosine theta. Since the displacement vector r is transformed into this manner under this rotation, we can generalize that any vector a would follow the same manner in such a way ax prime, the new coordinates, equal to ax cosine theta plus ay sine theta, and ay prime equal to minus ax sine theta plus ay cosine theta. Now the conclusion from all this, if the two components ax and ay do not transfer into this manner, they cannot represent components of a vector. Note, this is the transformation rule. Let's remember it. Example, determine whether x plus y and y minus x form a two-dimensional vector or not. So in this case here, ax equal to x plus y and ay equal to y minus x. Since ax prime and y prime must have the same form of dependence on x prime and y prime, therefore ax prime has to be in the same manner y prime, and a y prime equal to y prime minus x prime. And we just have the definition for x prime and y prime. If we substitute them back in this one here, we will get, remember, x prime equal to x cosine theta plus y sine theta, and y prime equal to minus x sine theta plus y cosine theta. Therefore, ax prime equal to x cosine theta plus y sine theta minus x sine theta plus y cosine theta, or we can rewrite it as x plus y, we just accumulated this one here with this one here, cosine theta and y minus x sine theta. Therefore, this one here is actually ax and this one here is actually ay. So ax prime equal to ax cosine theta plus ay sine theta. Now, if we follow the same procedure to find ay prime equal to minus x sine theta plus y cosine theta minus x cosine theta minus y sine theta equal to minus x plus y sine theta plus y minus x cosine theta, or minus ax sine theta plus ay cosine theta. As we can see here, upon transforming here, the new coordinates ax prime and ay prime follow the same rule as this one right here, which means x plus y and y minus x are components of a two-dimensional vector. Let's have another example. Determine whether x minus y and x forms a two-dimensional vector. Now, to solve this one here, in this case, ax is actually x minus y and ay equal to x. So in this case, this one here, ax prime equal to x prime minus y prime, and ay prime equal to x prime. And remember, x prime equal to x cosine theta plus y sine theta, and y prime equal to minus x sine theta plus y cosine theta. If we substitute this back in this one here, we will get ax prime equal to x cosine theta plus y sine theta plus x sine theta minus y cosine theta, or x minus y cosine theta plus x plus y sine theta. And from this result here, we can say that back here, ax in this one here equal to x minus y, which has no problem in this one here, but x plus y is not equal to ay, as ay, as we define it here, equal to x prime. So the conclusion for this one here, x minus y and x does not form a vector. No need actually to go further, as one component, ax prime, does not transform in the same way as x prime. Now, to go further and discuss three-dimensional vectors. Now, in three dimension, two axes rotate around the third one. So for instance, x and y will rotate around the z-axis. That's what we just discussed in the previous examples. Now, if, for instance, y and z rotates around the x-axis, or z and x rotate around the y-axis, we will follow the same procedure with some modifications. To understand this, let's have an example. Determine whether y squared plus x squared and minus xy and minus xz satisfy the vector transformation rule for rotation about each of the three coordinates. Just quick reminder for the procedure we mentioned before, this is x and y rotated around the z-axis perpendicular to the page. So in this case here we just discussed how the new coordinates x prime, y prime related with the original coordinates x and y. Now, if we would like to rotate the coordinates, let's say for instance, around the x-axis, so instead of using x and y in this case here, we should use y and z. Now, just let's have this trick. For instance, so x prime equal to x cosine theta plus y sine theta, and y prime equal to minus x sine theta plus y cosine theta. This is rotation around z-axis. But if we want to rotate the coordinates around the x-axis, so let's write here around x-axis, we will follow the same procedure as we mentioned here, but rather than using x and y, we will use y and z. The definition will be almost the same, but instead of x, replace each x with y and each y with z. So in this case here, so y prime equal to y cosine theta plus, rather than using y, it's z sine theta. And y prime, it's actually z prime, the new coordinate, equal to minus y sine theta plus z cosine theta. We can prove this, by the way, using the same graph as this one here. No need to do that again, but this is the method. Now, if we would like to rotate the coordinates around the y-axis, so around y, in this case, remember it's 1, 2, 3, x, y, z. So y should be replaced by z, and z should be replaced by x. So z prime equal to z cosine theta plus x sine theta, and rather than using z, we should use x prime equal to minus z sine theta plus x cosine theta. Again, we can use the same figure, this one here, but instead of x and y, the coordinates or the new coordinates will be x and z. Remember, in all the three cases, if we rotate around the, for instance, around the z-axis, in this case here, z prime should be equal to the same as z. Now, if we rotate around the x, so in this case, x prime will be equal to x, and around y, so y prime equal to y. Now, back to the example, determine whether y squared plus x squared minus xy minus xz satisfy the vector transformation. Let's start with rotation around the x-axis. Here, rotation around x-axis, and this is the transformation rules around the x-axis. ax equal to y square plus x square, ay equal to minus xy, and az equal to minus xz. Therefore, ax prime equal to y prime square plus z prime square, or y square cosine square theta plus x square sine square theta plus 2yz sine theta cosine theta plus y square sine square theta plus z square cosine square theta minus 2yz sine theta cosine theta. So after all, we just simplify this one here, y square plus z square. So ax prime is actually equal to ax. So the first point here satisfy the vector transformation. However, we're not done yet. Now, ay prime equal to minus x prime y prime. You just substitute by x and y in this case here. So it's equal to minus x. Remember, around the x-axis, x prime is x. So we just substitute by x. And y prime is y prime right here. So it's equal to y cosine theta minus xz sine theta, or it's equal to ay cosine theta plus az sine theta. Therefore, ay prime transforms in the same manner as y prime. Now, the third point, az prime equal to minus x prime z prime, which equal to xy sine theta minus xz cosine theta. Or in other words, it's minus ay sine theta plus az cosine theta. And again, az prime transforms in the same manner as z prime. So around the x-axis, yes, satisfy the vector transformation. But again, we are not done yet. We have to prove it around the y-axis and around the z-axis. From the above, y square plus z square minus xy and minus xz satisfy the vector transformation rule for rotations about the x-axis. Now we need to check if these vectors satisfy the vector transformation, if rotations around the y-axis satisfy the vector transformation rules. So the second step is rotation around y-axis. Now, this is the transformation rules around the y-axis, z prime and x prime. Now, let's check the first point, ax prime. Ax, it's equal to y square plus z square. Now, ax prime equal to y prime square z prime square. Now ax prime equal to, now let's substitute z prime with this one here and y prime with this one here and see what's going to happen. So y square plus x square sine square theta plus z square cosine square theta plus 2x z sine theta cosine theta. And from this one here, we can see that ax prime does not transform in the same manner as x prime, and we can stop right here. No need to go further to find the ay prime and az prime. Now, rotations around the z-axis, this part is similar to previous one, and the component do not satisfy the vector transformation. You can double check that. Now, let's define vector multiplication. Now, vectors can be multiplied in two methods: scalar product, and sometimes it's called dot product, and vector product, sometimes it's called cross product. Now let's start with scalar product or dot product. When you dot product two vectors a dot b, it's equal to magnitude of a magnitude of b cosine theta. Now, when you dot product two vectors, the answer is a scalar quantity. So a dot b is equal to scalar quantity. And the name scalar product comes from this definition. The dot product of two vectors, the answer is a scalar quantity. Based on this, when you dot product I dot I, so it's equal to the magnitude of I. The magnitude of I cosine theta is the angle between I and I, which is in this case 0, or I dot I, it's equal to the magnitude of I, it's 1 times 1, cosine 0, it's 1. So I dot I equal to 1. Same thing, j dot j, because both vectors in the same direction, so the angle between them, it's equal to 0. So j dot j, it's equal to 1. K dot k, again, it's equal to 1. But I dot j equal to, now the magnitude of I, it's 1. The magnitude of j, it's equal to 1. But the angle between I and j, it's 90 degrees. Cosine 90 equal to 0. So I dot j, 0. I dot k, same thing, 0. J dot k, 0. K dot I, 0. J dot I, 0. And K dot j, again, it's 0. So if we have two vectors, A, for instance, it's equal to AXI plus AYJ plus AZK, and vector B equal to BXI, BYJ, BZK, and A dot B, in this case here, we should have 9 components, but out of 9, only 3 components having magnitudes, which is I with I, j with j, k with k, and the other 6 components give us zeros. So when you dot product two vectors, you only multiply I with I, j with j, k with k, and remember the result is scalar quantity. So it should be equal to ax bx plus ay by plus az bz. One more thing we have to remember here is a dot b is actually equal to b dot a. So it doesn't matter actually a dot b or b dot a, you will get the same answer, which means a and b are commute, and a dot b plus c, in this case here, we can dot product a with b and dot product a with c. The result can be added, so we can say a dot b plus a dot c, and this is known as distributive law. As a real example for dot product is work. So work in physics is defined as F dot D or equal to F D cosine theta. In such a way, theta here is the angle between F and D. Example: what is the angle between the two vectors A 9i plus j minus 6k and B 4i minus 6j plus 5k? Now remember, A dot B equal to magnitude of A, magnitude of B, cosine theta. Now from this one here, cosine theta, it's equal to A dot B divided by magnitude of A, magnitude of B. Now let's find magnitude of A, which is equal to 9 square, it's 81, plus 1 plus 6 square is 36, all to the power half, or in other words, square root of 118. Now B in magnitude, it's equal to, same procedure, 16 plus 36 plus 25 to the power half, or 77 to the power half. Now use these to find cosine theta equal to ax bx plus ay by plus az bz divided by the magnitude of A, magnitude of B. So cosine theta, after all, will be equal to 36 minus 6 minus 30 divided by 118 times 77, all to the power half. You do the math. 36 minus 6, it's 30 minus 30, it's equal to 0. Cosine theta equal to 0. In this case here, theta is actually equal to pi over 2. This is actually an interesting result, as A and B are perpendicular or orthogonal to each other. So A and B are orthogonal. We also can conclude that if, and this is very important note here, If vector A is not equal 0 and vector B is not equal 0, and we found that A dot B equal 0, this means the vectors A and B are orthogonal. Now let's move to the other part of vector product, is cross product or vector product. When you cross product two vectors, the answer is a new vector which is perpendicular to the original vectors A and B. In other words, A cross B equal to a new vector C, and this C here is perpendicular to A and B. And from this one here, the name cross product or vector product comes from the result is cross product of two vectors is a new vector. Now let's assume we have here two vectors, vector A and vector B. So this one here is vector A and this one here is vector B. When you cross product A cross B, the answer is vector C. This data like this one here. Now, if we would like to find B cross A, the answer will be minus C. So B cross A, the answer will be minus C. To understand this very well, we can use right hand rule, or we can simply use like 1, 2, 3 rule. A, B, C. If you move with the same arrangement in this one here, the cross product will be positive. So A cross B is C. In this case here, it's positive. Now A cross B, it's C. B cross C, it's A. Now C cross A, it's B. So if you move this cyclic 1, 2, 3, A, B, C, the answer is positive. Otherwise, the answer is negative. Now B cross A. Now remember, after B it's C, it's not A. So B cross A, the answer is minus C. And C cross B, remember after C it's A. So C cross B, it's minus A. Or you can say this. Now A cross B, the magnitude here, it's equal to magnitude of A, magnitude of B, sine theta. Now, based on this definition, I cross I equal to, now the magnitude of I and I, it's just 1 here, but the angle between I and I, it's 0. So sine 0 equal to 0. So this one is 0. And J cross J, for the same reason, equal to 0. K cross K, again, it's equal to 0. Now, I cross J equal to a new vector perpendicular to them. And remember, it's cyclic. After I, it's J. So in this case, it's positive K hat. Now, J cross I, in this case, after J, it's K. It's not I. The answer is minus K hat. Again, J cross K, after J, it's K. So the answer is I. And K cross J, again, it's minus I. Now, K cross I, it's J. And I cross K, it's minus J. Now, if we cross product two vectors, in this case here, we should get 9 components, 3 of them it's equal to 0 and 6 of them it's not 0. Now to remember this one here, let's just have this quick sketch here, assuming that this is I and j, k. If you move this way, the answer is positive. If you move this way here, the answer is negative. Let's see, I cross j, it's k, and j cross k, it's I, k cross I, it's j, and so on. But I cross k, it's minus j, k cross j, minus I, j cross I, minus k. A physical example on vector product is torque. So torque is defined as R cross F. Example, find A cross B in such a way A equal to 2I 2j minus 10k, b equal to minus I plus j plus 5k. To find A cross B, the easiest way is to open a determinant like this one here. The first row, you just type I, j, k. Now, the second row is the components of the first vector, which is in this case A, 2 minus 2 minus 10, 2 minus 2 minus 10, and B, or the third row, is the components of the second vector, which is in this case minus 1, 1, 5. Minus 1, 1, 5. Now to find the result of this determinant here, you hide this row and hide this column. And remember, as you can see here, the common one here, it's I. You multiply this with this minus this with this. So it's 5 times minus 2 minus 1 times minus 10, it's minus 10, minus minus, it's plus 10. Now the second component should be negative. We will see later on why it's negative. You cover this one here with this one here. Now, as we can see here, it's j times, you multiply this with this, 5 times 2, it's 10, minus this times this, minus 1 minus 10, it's 10, so minus 10. The third component is, let's see, you cover this one, this row, with this column, and you multiply this with this, minus this with this, you will get k. Now 1 times 2, it's 2, minus 1 minus 2, it's 2 minus 2. So the result equal to 0. So A cross B equal to 0. Now, things we can conclude from this result here: if A cross B equals 0, but A is not equal 0, neither B not equal 0, then AB sine theta equals 0, and from this one here, theta could be 0 equal to or pi. In such a way, the angle between A and B is pi, and it means A is anti-parallel to B. Example, prove that if A is parallel to B, as vector here, then AX over BX equal to AY over BY and equal to AZ over BZ. Solve this one here. Since A is parallel to B, this means A cross B equals 0, and let's find A cross B in determinant equal to I J K AX AY AZ BX BY BZ. Now let's follow the same procedure as in the previous example. We will find that I AY BZ minus AZ BY minus J hat AX BZ minus AZ BX plus K AX BY minus AY BX all equal 0. Since it's all equal 0, it means that each component equal to 0, and from this one here we can say that AY BZ minus AZ BY equal to 0, and AX BZ minus AZ BX equal to 0, and AX BY minus AY BX equal to 0, and from this one here we can conclude that AY over BY equal to AZ over BZ, and AX over BX equal to AZ over BZ. And after all, we can say that AX over BX equal to AY over BY or equal to AZ over BZ. The division of a vector by another vector is not uniquely defined unless they are parallel or anti-parallel. So we don't have a general definition of division of a vector by another vector. So no general definition of division of a vector by another vector unless they are parallel or anti-parallel. Now let's move to triple product. In triple product, let's start with triple scalar product. For instance, D equal to A dot B cross C. In this case here, there is no need to include parentheses because B cross C is a vector quantity. This one here is a vector quantity. So A is a vector, B is a vector, C is a vector. So B cross C is a vector quantity. So A, which is a vector, dot another vector in this one here. But if we, for instance, include parentheses in this one here, it has no meaning whatsoever, because A dot B is a scalar quantity, and a scalar cannot be cross product with a vector, so you cannot do this. From now on, D equal to A dot B cross C, so the priority here is for the cross product, then the dot product. To do this one here, D equal to A dot B cross C, you can do this quickly by using the determinant in this one here. The first row here is the components for the first vector, which is in this case here AX, AY, AZ. Now the second row is the components for the second vector bx, by, bz, and the third one cx, cy, cz. It's good to mention that A dot B cross C in this one here equal to C dot A cross B, which also equal to B dot C cross A. So it's cyclic. Now you can move this one here, and keep the arrangement for them. One more note here. A dot B cross C, in this case here, it's equal to A cross B dot C. Again, the priority here for the cross product, then the dot product. Let's have an example. If we have A as a vector 3i minus 2j plus 6k, B equal to minus 2i plus 3j minus 4k, and C equal to I plus j minus k, find A dot B cross C. To find this one here, A dot B cross C, again, you open a determinant, like in this one here, and the first row here is the components for the first vector, which is in this case 3 minus 2 minus 6. The second one for the second vector, which is the component for the second vector, which is minus 2, 3, and minus 4. And the last one, it's 1, 1, minus 1. You follow the same procedure. You just hide this one and hide this one, and the result will be equal to 3 times 1 plus 2 times 2 plus 4 plus 6 minus 2 minus 3, and in total it's minus 15. Now the other type of triple product is triple vector product, like this one here. D equal to A cross B cross C, and it's very important here to define the parentheses, because parentheses here take the priority. In other words, there's a big difference between this one here is not equal to A cross B cross C. Therefore, parenthesis here is very important. It's unlike the other one, which is A dot B cross C. No need for parentheses, as we mentioned before. Now, to find this one here, we have to find B cross C first, then the result make cross product with A. Now, for this one here, B cross C equal IJK BX BY BZ and CX CY CZ. When you do this one here, you will find it's equal to I BY CZ minus BZ CY minus J BX CZ minus BZ CX plus K hat and BX CY minus BY CX. Now the result, which is this one here, you cross product with A, so A cross B cross C will be equal to again, open a new determinant, this one here, I, J, K. Now the second row is the component for A, which is AX, AY, AZ. And the third one is the components here. In other words, this one and this and this. So it will be BY CZ minus BZ CY minus BX CZ minus BZ CX, and the last one, which is the Z, BX CY minus BY CX. Now, upon following the same procedure to solve this determinant here, I will jump to the conclusion directly here. You can practice this, like A cross B cross C equal to B A dot C minus C A dot B. And this is called back tab rule. And it's very important rule. As a quick application for this rule, let's have this example. Show that A cross B cross C cross D equal to A dot B cross D times C minus A dot B cross C times D. Now to solve this one here, let's use the back tab rule, this one right here. But in this case, let's assume that A cross B equal to M. And upon substituting this one here, this will be M. So the equation here becomes similar to this one here. We can apply directly the back tab rule. So in this case, A cross B cross C cross D should be equal to C M dot D minus D M dot C. And let's just substitute back, instead of M using A cross B, C A cross B dot D minus D A cross B dot C, which equal to C A dot B cross D minus D A dot B cross C, and that's it. Now let's define a very important vector in physics, which is a del operator. Now this vector here is defined as like this one here, this simple. It's called del operator. Now the most unique thing of this operator, it's a vector, and when it comes to quantities, it modifies, it changes, and every time when this vector applies to any quantity, it produces special quantity in physics. Now this del operator here is equal to partial x I hat partial y j hat partial z k hat. Since this del operator is a vector, now three possible cases we have here. If this vector here applies to some scalar quantity, in this case here it's called gradient. And in this case here, gradient phi, it's equal to partial phi partial xi plus partial phi partial y j plus partial phi partial z k. Now the gradient of a scalar quantity is a great important in physics. As a definition here, E, or the electric field, it's equal to minus gradient phi, and phi in this case here is the potential. As another definition is F here, which is the force, it's minus gradient V here, and V here is the mechanical or potential energy. Now let's discuss properties of gradient phi. Properties of gradient phi. If we assume that phi here x, y, z is constant c, in this case, if we have here a surface, and this one here is the origin, and this is R, and this is P. Now phi is some constant here. The position vector R equal to xi plus yj plus zk, and dr in this case it's equal to dxi plus dyj plus dzk. Since phi is constant, d phi is equal to 0, or we can say that d phi is equal to gradient phi dot dr, which is equal to 0. From this one here, we can conclude that gradient phi is perpendicular to dr. Let's have an example. Find a unit vector perpendicular to the surface x squared plus y squared plus z squared equal to 3 at the point 1, 1, and 1, and derive the equation of the plane tangent to the surface at 1, 1, 1. Now to find the unit vector perpendicular to the surface. Now let's find here gradient phi equal to, this is phi, so the gradient d by dx, which is in this case 2x I plus 2yj plus 2z k. Now the unit vector, let's name it n here, equal to the vector itself over the magnitude for that vector. So equal to 2x I, 2yj, 2z k divided by square root of, now square root 2x square, which is 4x square plus 4y square plus 4z square. N at the point 1, 1, 1 equal to I plus j plus k divided by square root of 3. And this is actually a unit vector perpendicular to this surface right here. To derive the equation of the plane tangent to the surface at the point 1, 1, 1, let's define r minus r prime, which is in this case here, r is the position vector x minus 1 I plus y minus 1 j plus z minus 1 k. Now n is the normal at point 1, 1, 1, which is given in this part right here. Now n 1, 1, 1 equal to gradient phi at the point 1, 1, 1, which is equal to 2i plus 2j plus 2k. Now since n at the point 1, 1, 1 and r minus r prime are perpendicular to each other, which means n dot r minus r prime has to be equal to 0. In other words, 2i, 2j, 2k dot x minus 1 I, y minus 1 j, z minus 1 k equal to 0, or 2x minus 1 plus 2y minus 1 plus 2z minus 1 all equal to 0. Remember, when you dot product two vectors here, the answer is scalar quantity, and in this case here you can say that x plus y plus z, after rearranging this equation here, x plus y plus z all equal to 3. Let's have another example. If you have a vector r minus r prime equal to x minus x prime I plus y minus y prime j plus z minus z prime k, find gradient r minus r prime, this is A, and B, find gradient 1 over r minus r prime. Now before going further in this one here, these two quantities are very important quantities in electrodynamics, so let's find them. First, let's find gradient r minus r prime. Now, to find this one here, let's first find r minus r prime, which equal to x minus x prime square plus y minus y prime square plus z minus z prime square, all to the power half. Now gradient for r minus r prime equal to, now the gradient here, or the del operator, equal to partial x I partial y j partial z k. This one here applies on this one, x minus x prime square plus y minus y prime square plus z minus z prime square, all to the power half, equal to half x minus x prime square plus y minus y prime square plus z minus z prime square, all to the power minus half times 2 x minus x prime I plus half, same thing here, x minus x prime square y minus y prime square z minus z prime square, all to the power minus half times 2 y minus y prime j hat plus half, same thing, x minus x prime square plus y minus y prime square plus z minus z prime square, all to the power minus half times 2 z minus z prime k hat. Upon simplifying all this thing here, you will get gradient r minus r prime equal to x minus x prime I plus y minus y prime j plus z minus z prime k, all divided by x minus x prime square y minus y prime square z minus z prime square, all to the power half. Or now remember, x minus x prime I hat, y minus y prime j hat, z minus z prime k hat is actually r minus r prime, and the denominator here is the magnitude for r minus r prime. And this is a very important and unique result. Gradient for r minus r prime is equal to r minus r prime divided by the magnitude for r minus r prime. This has to be vector. And this result here is actually the unit vector in the direction of r minus r prime. Now let's find the other quantity b, which is gradient 1 over r minus r prime this equal to gradient x minus x prime square plus y minus y prime square plus z minus z prime square, all to the power minus half partial x I partial y j partial z k. When it applies on this one here, x minus x prime square plus y minus y prime square plus z minus z prime square, all to the power minus half. This equal to minus half times x minus x prime square plus y minus y prime square plus z minus z prime square, all to the power minus 3 over 2 times 2 x minus x prime I plus almost the same procedure as the previous one minus half times x minus x prime square plus y minus y prime square plus z minus z prime square to the power minus 3 over 2 times 2 y minus y prime j hat plus minus half x minus x prime square y minus y prime square z minus z prime square to the power minus 3 over 2 times 2 z minus z prime k hat. Upon simplifying this one here, gradient 1 over r minus r prime is equal to minus r minus r prime to the power 3. Again, this is a very important result. It's used very often in electrodynamics. Example: find gradient A dot R, and assuming that A is constant vector. Now to find gradient A dot R, in this case here, partial x I partial y j partial z k. Now A is actually a constant vector, so this del operator has no effect on A, it has only effect on R. Now the position vector here, it's actually equal to x plus y plus z. You apply this one here, you will get axi plus ayj plus azk, which actually equal to vector A itself. Now let's define differentiation of a vector. The rule is very simple for this one here. So d by dx, for instance, if we would like to find the derivative for the cross product A cross B, in this case here, so we apply the derivative for the first one and we apply the derivative for the second one. It's very important to keep the order. So dA equal to dx cross B plus A cross dB by dx. Again, the order here is very important. Assuming that A equal to A hat A, in this case dA by dx is equal to d by dx A hat A, or equal to dA by dx A plus A hat dA by dx. This relation is convenient in some cases to find the derivative of any vector. So in the case of Cartesian coordinates, assuming that A as a vector equal to AXI plus AYJ plus AZK, in this case here, dA by dx equal to dA by dx I plus dA y dx by dy j hat plus dA z by dz k hat. As a physics example for this derivative of vector is the derivative of position vector. dr by dt is actually equal to velocity or r dot, and again the derivative of velocity v is acceleration, so a actually equal to dv by dt, or in other words it's v dot. Now let's define vector integration. The first vector integration is the line integral. Example like this one here, integration phi dr or integration f dot dr, closed surface here, and integration f cross dr. Starting from the first one, this one right here, integration phi dr equal to integration phi I dx plus j hat dy plus k hat dz, and upon simplifying this one here, it's equal to I integration phi dx plus j integration phi dy plus k integration phi dz. Now this integral here is actually work. We are familiar with this definition here, which is work equal to integration f dot dz. r. Let's have an example. Evaluate the integral 0 to 1 xy plus y square dr along the paths 1. A straight line from 0 to 1 0 and then 1 1. Now the second integral along a straight line from 0 to 1 and then 1 1. The last one is straight line from 0 to directly 1 1. Now let's start with the first one. The integration is 1 from 0 1 1 xy plus y square I dx plus j dy equal to I from integration from 0 y equal to 0 to 1. The function is xy plus y square dx plus the second part of the integral j hat from 0 x equal to 1 here xy plus y square dy. Now the reason we identify this one here is, now here's the coordinates we have here. Now this one here is 0 0. Now the first path, this one here, straight line from 0 to 1 0, so you move right here. This is 1 0 and moving to 1 1. So the integral is actually the first one, y equal to 0, the first part of the integral, y equal to 0 right here, and x equal to 1. And the second part of the integral, it's over the y-axis, and in this case x equal to 1 right here. The initial part, the lower limit of the integral, y equals 0 and x equal to 1 to 1 in this case here along the y-axis. Now the first integral 0 y equal to 0 1 xy plus y square dx equal to 0, because y equal to 0. Now if we substitute y equal to 0, so the integral equal to 0. Now the second part, which is in this case here from 0 x equal to 1 here, xy plus y square dy, this one here equal to, we should substitute x equal to 1 because it's constant, It's not changing over the y integral. So from 0 to 1 here, y plus y square dy or equal to y square over 2 plus y cube over 3 from 0 to 1, and this whole thing equal to 5 over 6. Now the integration from 0 0 to 1 1 for xy y square I dx plus j dy equal to 5 over 6 j hat. Now to find the integral along the path, this one right here, 0 0 to 0 1 and 1 1. Now quick sketch here. Here's the coordinates, this one here. This is 0 0, 0 1 and 1 1. In this case here, x equal 0 and y in this case equal to 1, 0 1 right here. So the integration 0 0 to 1 1 along the other path xy plus y square dr is actually equal to, now be careful here, the first part of the integral, it's along the y-axis, so it's j hat integration from 0 to x equal to 0 and 1. Now x equal to 0, it's fixed here, and the changing only on y from 0 to 1. This is 0 0. So y is changing from 0 to 1, but x is keeping constant. xy plus y square dy plus I, now along the x-axis, now x is changing from 0 to 1, but y is constant, which is equal to 1. So integration from 0 to 1, but y equal to 1 is here. xy plus y square dx. Upon simplifying this one here, j integration from 0 to 1 y square, this one right here, dy, because we substitute x equal to 0 in this one here, so this part here cancel out. So y square dy with j hat plus I integration from 0 to 1 x plus 1 dx equal to j y cube over 3 from 0 to 1 plus I x square over 2 plus x from 0 to 1. In total, it's equal to 1 over 3 j hat plus 3 over 2 I. Now to find the integral directly from 0 0 to 1 1, so if you have just quick sketch here, this is 0 0 and this is 1 1, like this. Now the integration from 0 0 1 1 in this case here, xy plus y square dr equal to I integration from 0 to 1 xy plus y square dx plus j hat integration from 0 to 1 xy plus y square dy equal to I integration from 0 to 1 x square x cube dx here plus j hat integration from 0 to 1 y square plus y square dy. Now what we did in this one here, if we look at this one here, this is a linear equation, and y in this case is equal to x. So if x equal to 0, y is equal to 0. If x equal to 1, y equal to 1. In this case, in the first integral, we replaced y by x. For that reason, we got here x squared, and this is actually x squared, it's not cube. We got actually x, and we replaced y by x, so x squared, and rather than using y squared, we just used x squared dx. And the same thing we used in this one here, xy, rather than using x, we used y, so it's y squared plus y squared dy. Now simplifying this integral, you will get 2i x to the power 3 over 3 from 0 to 1 plus 2j from y cubed over 3 from 0 to 1. This equal to 2 over 3i plus 2 over 3j. Now, the reason for doing this integral in different paths to prove that the integral is path dependent, because for the first path, the integral equal to 5 over 6. The second path, the integral equal to 1 over 3 j hat plus 3 over 2 I hat. Now, the third path, the integral is equal to this one here. Now let's have another example. Now in this example, find the work done by the force. It's given like this one here. It's I hat y over x squared plus y squared minus j hat x over x squared plus y squared in moving the object around the unit circle in the xy plane, first counterclockwise from 0 to pi and clockwise from 0 to pi. Now let's find the work done here if the object is moving counterclockwise from 0 to pi. Work is equal to integration f dot dr. Now in this one here, integration I y over x squared plus y squared minus j x over x squared plus y squared dot r I dx plus j dy. This equal to integration y over x squared y squared dx minus integration x over x squared plus y squared dy. Now, rather than using Cartesian coordinates, let's use polar coordinates. Since the object is moving in a circular path, like this one here, if this is the coordinates here, the position with this one here, it has intercept with the x-axis and intercept with the y-axis. So x for this one here, if this is theta, x for this one here equal to r cosine theta, and r in this case is the radius for this circular path, and dx will be equal to minus r, because r is constant, sine theta. Y in this case is equal to r sine theta, and dy equal to r cosine theta d theta, this one d theta as well. Now x square plus y square, it's equal to r square. You substitute all these things in this integral right here, you will get work equal to integration. Now it's from 0 to pi r square sine square theta d theta divided by r square minus integration from 0 to pi r square cosine square theta d theta divided by r square. After all, the work will be equal to integration from 0 to pi. This is minus, by the way. Take the minus out and use the identity sine square plus cosine square, it's equal to 1. So work will be equal to minus integration from 0 to pi d theta, or upon integrating this one here and substituting the limits, the work will be equal to minus pi. Now for the second case, clockwise from 0 to minus pi, we will follow the same procedure. Nothing will change from this here, but the limits of the integral. So work equal to integration from 0 to minus pi minus d theta, which equal to integration from 0 to pi, this one here, d theta, and this equal to pi. Back to the del operator, this one. We mentioned that the del operator may apply on a scalar quantity, and this quantity is called gradient, like gradient phi. As another application for del operator, when it applies on another vector with dot product, this quantity here is called divergence. The concept of divergence is very important to understand the idea of a source and a sink in physics. And divergence A, and remember, this is a vector and this is a vector, and the result is a scalar quantity because it's a dot product. It's equal to partial x I hat partial y j hat plus partial z k hat. This is the del operator, dot a as a vector, ax I hat ay j hat az k hat. And remember, when you dot product two vectors, u dot product I with I, j with j, k with k. Therefore, divergence A is equal to partial AX partial X plus partial AY partial Y plus partial AZ partial Z, and this is scalar quantity. As a real example in physics is divergence E, this one here, equal to rho over epsilon naught, and this one here you will find it in electrostatics. As another example in magnetism is divergence B, in this case, if it's equal to 0, that means there is no source or sink, and this is the fact that B is said to be solenoidal or divergenceless. Let's have an example. A rigid body is rotating with constant angular velocity omega. Show that the linear velocity v is solenoidal. Prove that v equal to omega cross r, in this case here, and open the determinant I, j, k, omega x, omega y, omega z, x, y, z. When you solve this determinant here, you will get here I z omega y minus y omega z minus j. You remember the rule how to solve this 3 by 3 determinant. Z omega x minus x omega z plus k hat y omega x minus x omega y. As we mentioned before, if a divergence of any quantity is equal to 0, then that quantity is said to be solenoidal or divergenceless. Therefore, divergence V equal to partial x for this part right here, z omega y minus y omega z minus partial y z omega x minus x omega z plus partial z y omega x minus x omega y. Since omega is a constant vector, then here partial z partial x will be equal to partial y partial x, or equal to partial z partial y, which equal to partial x partial y, which equal to partial y partial z, and equal to partial x partial z, all equal to 0, and therefore V is solenoidal. Another example right here, find divergence r hat over r square and find divergence r. Now, before going further, solve these quantities. Now, these quantities are very important in electrodynamics. Now, let's find divergence r hat over r square equal to divergence xi hat yj hat z k hat divided by x square y square z square to the power 3 over 2, which equal to partial x divided by x square y square z square to the power 3 over 2 plus partial y, same rule here, x square y square z square to the power 3 over 2 plus partial z over x square y square z square to the power 3 half, this one here. Now partial x over x square y square z square to the power 3 over 2 is actually equal to 1 over x square y square z square to the power 3 over 2 minus 3x square divided by x square y square z square to the power 5 over 2. And upon simplifying this one here, remember x square y square and z square here, it's actually equal to r square, and this thing here it's equal to 1 over r cube minus 3x square divided by this one here, it's equal to r square, and this will be r to the power 5. If we follow the same procedure for this part here, this one here, you will find partial y divided by x square y square z square to the power 3 over 2 will be equal to 1 over r cube, same rule here, minus, instead of x we will use y, 3y square over r to the power 5. And the last term, partial z over x square y square z square to the power 3 over 2 will be equal to 1 over r cube minus 3z square over r to the power 5. Now upon adding this one with this one and this one here, the result will be divergence r hat over r square, which equal to divergence. Now instead of using r hat, we can use it the vector divided by its magnitude, so it will be r over r cube here equal to, now 3 over r cube minus 3r square, because x square plus y square plus z square it's equal to r square over r to the power 5. And upon simplifying this one right here, you will get 3 over r to the power 3 minus, now r square with r to the power 5 will be 1 over r cube, so 3 over r cube, and after all the result will be equal to 0. Now let's find the divergence r. Let's follow the same procedure. Partial x I hat plus partial y j hat plus partial z k hat dot, The position vector r, it's xi hat, yj hat, zk hat, and partial x, for x it's equal to 1, plus partial y, for y it's equal to 1, partial z, for z it's equal to 1. So the answer will be equal to 3. Divergence r is actually equal to 3, and this is another important quantity in physics. Let's define Gauss's divergence theorem. Now, Gauss's divergence theorem states that the integration, closed integral here, v dot d area is equal to integration over the volume divergence v d tau. In Gauss's divergence theorem, rather than using the surface integral, we convert that integral into divergence and over the volume. This is the meaning of this Gauss's divergence theorem. As an application for Gauss's divergence theorem, let's have this example. Evaluate the integral r dot dA over the unit cube defined by the point 0, 0, 0 and the unit intercepts on the positive x, y, and z axis. Here's the situation. This cube here. The origin is 0, 0, 0, and the intercept with the x-axis, it's 1, 0, 0, and on the y-axis, 0, 1, 0, and on the z-axis, it's 0, 0, 1. Now, to find the integral in this one here, we have to find the integral over all the surfaces here. And this cube has 6 surfaces. So let's start with them. Integration plus surface r dot d area, it's equal to integration r dot d area. This is the, let's name it front wall, the one front wall, plus integration over back wall. Same thing, r dot d area plus integration over top wall, r dot d area plus integration over bottom wall, r dot d area plus r dot d area plus integration over right wall, r dot d area. Now let's start with them one by one. Integration over front wall, r dot d area is equal to, now this is the area, so it has to be double integral. This is the front wall, this one here, right here, this one here, and the area, it's in the YZ plane, this one here. So it will be, now from 0 to 1, from 0 to 1, r is actually equal to xi hat, yj hat, zk hat, and the area is the area element here, it's equal to dy dz. And don't forget the dot here between r and the area. So the area vector is perpendicular to this one here, which is in the x-axis. So this will be here I hat. Now there's no j hat, no k hat in this one here. So when you dot product this with this, you will get double integral from 0 to 1, 0 to 1, x dy dz, and this actually equal to, now x is independent on y and z. In this case here, it's equal to x double integral from 0 to 1, 0 to 1 dy dz, and the integration of dy, it's y, 0 to 1, it's just 1, and integration of dz here, it's z, the integration from 0 to 1, so it's 1, and x in this case for the front wall, it's 1, so this whole integral here, it's equal to 1. Therefore, the integration over front wall r dot d area is equal to 1. Now let's find integration for the back wall r dot d area. Now let's follow the same procedure for this one here. This is the back wall, this one. This light blue one, this is the back wall. Now integration r dot d area is equal to double integral 0 to 1, 0 to 1. Now same rule here, x I hat, y j hat, z k hat. Now dot the d area, it's the area vector which is in the negative side, it's minus I hat dy dz. Now the x position for the back wall, it's equal to 0, so this one here, it's equal to 0, and if you dot product this with this, no j hat, no k hat with this one here, and the only one that multiply with the I hat is equal to 0, so this whole integral, it's equal to 0. So integration r dot d area for the back wall equal to 0. Let's find the integration for r dot d area for the right wall, and if we follow the same procedure, we will get that it's equal to 1, and integration left wall r dot d area equal to 0, integration for r dot d area for the top wall equal to 1, and integration for r dot d area for the bottom wall equal to 0. Remember, we just use the same rule as in the front and back wall calculations. After all, the total integral over closed surface r dot d area is equal to 1 plus 0 plus 1 plus 0 plus 1 plus 0. So all this thing here, it's equal to 3 units. Fortunately, with the aid of Gauss's divergence theorem, we can solve this one in just 2 simple steps. Now let's remember Gauss's divergence theorem here, another method. Gauss's divergence theorem, the closed surface r dot d area, it's equal to integration divergence r d tau, and this is over the volume. Now divergence r, we just proved this one few minutes ago in this one here. It's just back here. Now this one here, we just proved this one here. So divergence r, it's equal to 3. So integration closed surface r dot d area is actually equal to integration 3d tau, and d tau here it's equal to dx dy dz from 0 to 1, and the integration of dx from 0 to 1 it's equal to 1, integration of dy from 0 to 1 it's equal to 1, and integration from 0 to 1 for dz equal to 1. d tau here equal to dx dy dz. So all this d tau integration it's equal to 1. So this whole thing it's equal to 3 units. So far we defined the del operator when it's applied on scalar quantity, and we name this gradient, and we defined the del operator when it applies on a vector, it's called divergence. Now let's discuss the curl when the del operator applies on a vector with cross product, and this quantity here curl A is defined as curl A, and curl A equal to, now same rule as the cross product, I j k partial x. Remember, the second row is the components for the first vector, which is partial x, partial y, partial z, and a in this case here it's equal to ax, ay, az. Let's have an example. A rigid body is rotating with constant angular velocity, which is omega in this case. Find curl V. Now let's find V is equal to omega cross r, and let's open the determinant. I j k omega x omega y omega z x y z. Therefore V equal to z omega y minus y omega z, this is I hat, plus z omega x minus x omega z, this is j hat, plus y omega x minus x omega y, and this is k hat. Now let's find curl V. Curl V equal to, again we have to open a determinant here, I j k partial x partial y partial z. Now the components for V, the x component, this one here, z omega y minus y omega z, z omega x minus x omega z, y omega x x omega y. Now upon solving this determinant here, we will get curl V equal to omega x plus omega x I minus omega y minus omega y j hat plus omega z plus omega z k hat. Now in total this is 2 omega x, 2 omega y, 2 omega z. So 2 times omega x I hat omega y j hat omega z k hat, or in total it's equal to 2 omega. As another example here, find curl r over r cube, and the solution for this one here, curl r over r cube, this one here, it's equal to, again open the determinant, I j k partial x partial y partial z. The x component for r over r cube is actually equal to x over r cube, and this is y over r cube, and this is z over r cube. Following the same procedure to solve the determinant, we will get curl r over r cube will be equal to 0. And again, this is very important result used in electrodynamics. Now, let's define another important theorem, which is called Stokes' theorem. Stokes' theorem states that integration over the surface curl f d area equal to closed integration f dot dl. Now, unlike Gauss's divergence theorem, we just convert area to volume. Now, this one here, we can convert length into area using this Stokes theorem. Example. If we have a vector t, which is equal to minus y I hat plus x j hat, with the aid of Stokes' theorem, show that the integral around the continuous closed curve in the xy plane is equal to 2a. So, with the aid of Stokes' theorem, t dot dl is actually equal to integration curl t dot d area. Now let's find curl t, this one, and open the determinant I j k partial x partial y partial z. Now t, the components here, minus y x 0. Upon solving this determinant here, you will get 1 plus 1 k hat, or equal to 2k hat. Now, d area is equal to d area k hat. So the area, it's in the xy plane. So the area vector, it's in the z hat or k hat. In this case here, integration t dot dl equal to 2k integration dot k d area, or k dot k is just 1, so 2 integration d area, and integration of d area, it's a. So the answer will be equal to 2a. Now, let's discuss successive application of the del operator. The first application of the del here, if we apply it on gradient. Now, the del operator, if we apply it on gradient, we have three possibilities. This gradient phi, gradient phi. Now, we can just directly apply the del on the gradient like this one here, and we can apply the del on the gradient like this one here, and we can apply the del operator on this one here like this one here. Now, in this one here, the first one, this is a vector and this is another vector. Now, a vector cannot be applied on a vector like this one here, so this is not possible. Now, a vector can be applied on another vector with a dot, and this is all right, no problem with that. And vector can be applied on another vector with a cross product. Again, this is no problem with that. So out of the three here, we have two possibilities of applying a del operator on gradient quantity, divergence of the gradient, or curl of gradient. This one, again, it's not possible whatsoever. So let's discuss these two possibilities. Divergence of gradient phi is equal to del square phi and equal to, now del square, it's partial to partial x square phi plus partial to phi partial y square plus partial to phi partial z square. And this quantity here is very important, again, in electrostatics, which called Laplacian. Therefore, del square, it's actually equal to del dot del. Now, let's discuss the curl of the gradient phi, this one here, equal to, again, open a determinant, ijk partial partial x partial partial y partial partial z, and gradient is partial phi partial x partial phi partial y partial phi partial z. When we solve this determinant here, you will find curl of the gradient phi will be equal to 0. Therefore, out of the three possibilities here, this one here, this one again, it's not possible at all. This one here, it's equal to 0. So out of the three possibilities, applying a del on a gradient is the Laplacian, which is this case here. Now, let's move with the other case, the divergence. When the del operator applies on the divergence, again, three possible cases we might have. So the del operator might be applied on three different cases. The first one, divergence A, and the second one, divergence A and divergence A, like this. Now, del might operate on this divergence with the quantity del, like del divergence A, or it might applies on this one here with divergence A, and the other one, which is applies with the curl, this one here, divergence A, this is curl. Now let's discuss the three possible cases we might have in this one here. Starting from this one here, now divergence A is a scalar quantity, and this is a scalar and this is a vector quantity. A vector cannot be applied on a scalar quantity with the cross product. So this case is not possible. Now again, the divergence A is a scalar quantity, and a vector quantity cannot be applied on a scalar quantity. So this another case is not possible. So the only case we might have is this one here, because divergence A is a scalar quantity and del can be applied on a scalar quantity directly like this one here. So out of the three cases, we only have one case, which is this one right here. Therefore, gradient divergence A equal to gradient partial AX partial X plus partial AY partial Y plus partial AZ partial Z, which equal to partial XI plus partial YJ plus partial Z K applies on partial AX partial X plus partial AY partial Y plus partial AZ partial Z. This equal to partial to AX partial X square plus partial to AY partial X partial Y plus partial to AZ partial X partial Z, all with I hat plus partial to AX partial Y partial X plus partial to AY partial Y square plus partial to AZ partial Y partial Z J hat plus partial to AX partial Z partial X plus partial to AY partial Z partial Y plus partial to AZ partial Z square, all K hat. Now let's move to the third possible case is the curl. Successive application of the del operator is the curl. Now let's see again. Applying a del operator on a curl quantity might have three possible cases. So a del operator might apply on curl A, curl A, curl A. Now a del here applies on a del on a curl here directly like this one here might be, and it might be applies on this with divergence of a curl like this one here, or might be applies on curl A. Now let's discuss the three possible cases here. Now the first case, curl A is a vector quantity and del is a vector quantity. A vector cannot be applied on another vector without dot or cross. So this case is not possible at all. Now the other case is curl A is another vector, and this vector applies with the del, the dot product, and this might possible case, and this one here. Now curl A is a new vector cross another vector. Again, this is a possible case. So out of the three, We might have two possible cases, and this case is not possible at all. Now let's discuss these two possible cases. The first one is the divergence of the curl A, and again divergence. Curl here, it's I, J, K, partial X, partial Y, partial Z, and AX, AY, AZ. Now, I will jump to the conclusion directly here. We have done this so many times. So the divergence for this curl here is equal to 0. Now, following the same procedure, curl of the curl A, this one here, will be equal to, I'll use back cap rule that we discussed before, and you can prove it. This one here, divergence A minus Laplacian A. So out of the three possible cases for the curl, this one here we found it is equal to 0, and this one here it's not possible, and this one here we used back cap rule to prove it, and it's equal to this quantity right here. Just let's rewrite this one here like Laplacian A, it's equal to this divergence A minus curl A. Now let's summarize the cases we have so far. Now a del can be applied on gradient with divergence. This one here, and we define this as Laplacian. And a del can be applied on gradient with a curl, and we found that this one equal to 0. And in case of divergence, the only possible case is a del can be applied on a divergence like this one here, and in case of curl, a del can be applied on a curl with two possible cases, dot, and this one here equal to 0, and a del can be applied on a curl with cross product, and this equal to divergence A minus Laplacian A. And so far, out of 9 possible cases, we only have this case and this case and this case. That's it. Thank you for watching.